Objective 3, 2.6, the student will be able to solve applications involving logarithms. Well, in order to be able to solve applications, you have to be able to solve equations. So let's look at this. Here's a logarithmic equation, and we're going to use properties of logarithms to make it more manageable. And we have here a sum of logs, and it would really be nice just to have one logarithm. Well, we know that the log of a product is the sum of the logs. And since we have a sum of logs here, we'll write it as the log of a product. So log, same base 4 of the product of the two arguments, x plus 6, x minus 6. That is the new argument. And all of that is equal to 3. Well, now we will change it to exponential form. So we have, well, it's that to the that equals that, right, in exponential form. So in exponential form, it's 4 to the 3 equals the argument x plus 6 x minus 6. 4 times 4 times 4 are 64. So 64 is equal to, well, now this is going to be a quadratic equation, right? We're going to have an x squared. So we're going to want to get everything on one side, and we're going to want to combine like terms. So foiling, we have x squared minus 6x plus 6x minus 36, and of course the 6x's cancel, and 64 is equal to, cancel, x squared minus 36. Of course, we might have used the property, the fact that the sum of the conjugates is the difference of squares. Well, we want to get everything on one side here, so we're going to add 36 to both sides. Actually, because there's no linear term, there's an easier way to solve this quadratic equation. We're going to be able to get to a square to both sides move. So add 36, add 36, and 100 is equal to x squared. And we're going to undo the squaring by taking a square root of both sides. Square root of both sides, square root of both sides, and when you take a square root of both sides, of course, one side is plus or minus. X equals plus or minus square root of 100, which are 10. X equals plus or minus 10. But we can see right off the bat that there's a big problem with negative 10. Negative 10 can't be a solution. You can't you know, put negative 10 in there or in there, because that would give you a negative argument or input of a logarithm. And the input of a logarithm must be positive. Now, if you have positive 10, you're okay on that account. Okay, so don't forget that fact that the argument of a log must be positive. Now, that doesn't mean that x always has to be positive. It usually will be, but it's possible to have a positive value of x. It's possible to have a negative value of x that still works. Okay, if we didn't have the second logarithm, it would still be okay to have, say, x equals negative 3. Then the argument of the first logarithm would be positive 3, because it would be negative 3 plus 6, which is 3. That would be okay. But the argument that the entire input of a logarithm must be positive, and so we could not have, and here we have 16 and 4 for these arguments. So we're going to have to reject the negative solution. We're going to keep the positive solution, 10, and that is the answer. Okay, so slash out that negative solution. The answer is x equals 10. To recap, these are the moves that were made. Okay, we used what's called the product rule, which I call the log of a product is the sum of the logs. I like to write that in words. Now, got to be careful, because what we really mean by this left-hand side here is that the argument of the logarithm is now a product. Okay. And then we simplify. X squared minus 36 is the same thing. Then what we did, the key move here, is we wrote the logarithmic equation as an equivalent exponential equation. And that is using the definition of the logarithm. Well, as we said, we simplified 4 cubed. We added 36 to both sides. Definition of the logarithm, that's really what happened up here. Took a square root of both sides. One side is plus or minus, but not the minus. X equals 10. We said the reason why it was 10 and not negative 10 is that you can't have non-positive argument of a logarithm. Another one. Log pi plus log 10,000 pi equals x. Okay. And what we really want here is a minus. We want this to be minus. Okay. So what I'm doing here is changing the problem. Okay. I didn't want it to be plus. So the problem is with the minus here, and so here we're going to use the rule that the log of a quotient is the difference of the logs. We have a difference or subtraction of logs. We're going to write as the log of a quotient. So log pi over, well, it's a quotient of the two arguments, so 10,000 pi. 10,000 pi. Now, when we say log, you might have thought, well, hey, there's no base to that logarithm. That's a problem. Okay. Well, there is actually a base. There's a default base. And the default base of a logarithm is 10. We call it a common logarithm. We're going to talk about that in a few minutes. Well, we can see how this thing is going to be simplified. We're going to be able to cancel pi top and bottom. Of course, all of this equals x. So we've got log, which is log base 10, 1 over 10,000. 1 over 10,000. Well, now we kind of see where this is going equals x, because we've got the base is 10 and the argument is a power of 10. Okay. Let's just say, okay, let's just talk about the 10,000. We know that's 10 to the 4th. So there are 4 zeros after the 1. Okay. But because 1 over a to the n, that's what is meant by a to the negative n, we really have the negative 4th power of 10. So log, it's base 10. We don't have to keep writing that, but just for clarity's sake I do. 10 to the negative 4. Okay, equals x. Now there's a property of logarithms. You know, hopefully, you know, we're kind of getting used to these things enough to be able to say, oh, well, the power that you raise 10 to get 10 to the minus 4 has to be negative 4. Okay? Remember, the logarithm is a power. The logarithm is an exponent. The exponent to which you raise the base in order to get the argument. Well, what power is it to which you raise 10 in order to get 10 to the minus 4? Well, obviously that's negative 4. X is going to be negative 4 here. Of course, that's why we made a property that log base a of a to the x equals x, where here a is 10 and x is negative 4. But negative 4 is the solution, and so yeah, we have x is negative in a logarithmic equation. We haven't made any argument of a logarithm negative, and so unless you do that, there is no problem with having x be negative. And so here we have a statement of common log. This says that the default base of a logarithm is 10. If you don't see a base, then the base is 10. There's always a default, right? Like if you have x, what is the default exponent? The default exponent is 1, right? What is the default coefficient? The default coefficient is 1. If you have square root of 2, what is the default index? Right? There's a default index to a radical. Well, the default index is 2. It's a square root that we're communicating, that we're taking there. when we take a square root. When we have the radical symbol without anything in there, we're saying that's a square root. The default index is 2. Well, the default base of a logarithm is 10. Natural log, we have a special way of writing that, and that is ln. Okay? That means it's log base e, where of course e is that number that we have learned about, which is approximately 2.72. And we use that one a lot. Natural logarithm, ln, that's the logarithm with base e. Solve for x. Obtain the exact solution of this equation in terms of e. Okay, so here we have a difference of logs, and of course it's the log of a quotient which is the difference of logs. So we can write the left-hand side as a single logarithm with the same base e. It's a natural logarithm, and the argument is the quotient of the two arguments. Now this should be plus right here. Okay. Well, what do we do with this? Take a moment to think about that. I'll give you 3 seconds. Of course, you could pause the video if you like, but what do you do with that? We're trying to find x, right? We're trying to solve for x. They also tell us that we should obtain the exact solution. Okay, it's not going to be a decimal at the end. An exact solution in terms of e. Well, remember that the base of the natural logarithm is e. We're going to write the equivalent exponential form. Okay, that to the that equals that. E to the 1 equals that x plus 1 over x. Okay. Well, how do we solve that? Well, we can't really deal with it if we have x in the denominator. So we want to get that x out of the denominator, and we'll do that by multiplying both sides by x. Then we can't really solve for x if we have x on both sides, not yet, and so we have to get x on the same side. Okay, so we multiplied both sides by x. Now we're going to subtract x from both sides to get x on the same side. And now we're able to make 1x out of that on the left-hand side. Okay, we are going to factor the x. That'll turn the two x's into 1x. We're going to factor the x out of xe minus 1x. And you realize that's the same thing, right? If we were to go backwards in this problem and distribute the x, we would have what we had in the previous step. So factor out the common factor, which is x, and now what we have is x times a number equals a number. You know, this is really no different than, you know, x times 5 equals 10. Okay, what would we do? We would divide both sides by 5. Divide both sides by 5, you know, x is 2 for that problem. Well, it's the same thing with this. X times a number equals a number. So we're going to divide both sides by the coefficient of x. The coefficient of x is the number e minus 1. What is e minus 1? Well, for e, which is approximately equal to 2.72, e minus 1 is going to be approximately equal to 1.72. So we're dividing both sides by that number. Divide both sides by e minus 1, and now we have x equals a number, and that is the solution. There's no better way to write that than 1 over e minus 1. Okay? We don't want to approximate. We don't want to go to the calculator because we were told in the instructions not to do that. It doesn't say, round your answer or get an approximation. It says give the exact answer. And any approximation is not exact. So the answer is 1 over e minus 1. Okay, here's a kind of real-life application. It has to do with money. That interest rate is not very much real life, 4%, but we'll go with it. How long will it take money to double if compounded monthly at 4% interest? Okay, so we're talking compound interest. So we're going to need the compound, we're talking compound interest, so we're going to need the compound interest formula. And there's our compound interest formula. Now, to work with it, we first realize that money is doubling here. How long will it take money to double? That is, your principal P, that's going to become double whatever P was. So instead of A, we're going to write 2P. And that has to do with the doubling right there. So that's always going to happen. Okay? And then, as often happens, we're going to divide both sides by P. Because P is multiplied by this big nasty exponential expression. Now of course we see how this expression, we have inserted values that are relevant to this problem. Interest is compounded monthly. That means that M equals 12. M, which used to be called N, the number of times per year interest is compounded, is 12. So that's why 12 appears right here. And T, that's what we're trying to find, right? How long will it take? That's what T is. So that's what we're going to try to find. And R, the interest rate, is 4%, which in a decimal, move the decimal 1, 2 to the left, 0.04, and that's why that number appears in the expression. Well, now we're trying to solve for T. We're trying to dig T out of there. And so we're going to divide both sides by P to dig out the T. Divide both sides by P, and on the left-hand side, the P's are going to cancel, and you're just going to have the 2. So that 2 is always going to appear in this money doubling problem. Okay? If money were being tripled, which happens sometimes, then a 3 would appear right there. Now, this number, if you have 1, let's just look at the inside. 1 plus 0.04 over 12. And so 4 is, of course, a third of 12. And so it's a third, except it's a third of 1%. So moving the decimal twice again, or just going to the calculator, 1.0033333. Now, they could have just done this, but apparently Barnett maybe didn't introduce this anywhere, and we know you know it. Probably would have been better just to write it this way. Anyway, that is an exact number, okay, because of the dots. If we didn't have the dots, then we'd be approximating something we don't want to do this early in the problem, because we're going to be using this number, this 1.003 repeating, and the more you use it, the more you compound the rounding error that you introduce when you round the very first time. That's why any rounding we do, we leave to the end. Well, now, how do you solve this equation? Okay, we've got an equation here. It's exponential. We've got the variable in the exponent. We really don't want that. And so what we do is we take a log of both sides. We're going to take a natural log of both sides, just because we like natural logs. And besides, it's easier to squeeze the ln in between the equal sign and the right hand side. So take a natural log of both sides, and then that 12t, well, here's where that key property of logarithms comes in. We were saying it's such a big deal, okay? And now here's where it comes in. We are able to take that exponent of the argument of the logarithm, 12t, and throw that thing down front as a cofactor of the logarithm. 12t times the logarithm. And so now we just have it's a linear equation. A number equals a number times the variable t times a number. Okay? And so it's a linear equation. It's no different than 5 equals 10 times x times whatever you want, 3. Okay? What would we do? Well, we'd probably call it 30, but we could hold off on doing that until we just divided both sides by 10 times 3, and that would isolate x. Okay, and that's what we're doing here. Okay, so that's another problem that's simpler. But we're just dividing both sides by the coefficient of the variable for which we're solving, which is t. Divide both sides by 12, ln 1.003 repeating both sides. 12 ln 1.003 repeating. Okay. Now we go to the calculator, and we have to make sure that we put parentheses around the denominator so we avoid an order of operations error. It's a good practice always to put parentheses around top and bottom when we're going to the calculator. We get a number 17.36. So it will take 17.36 years. 17.36 years is the amount of time it will take money to double if invested at 4% compounded monthly. So the strategy, you had to start it the right way. You had to replace a with 2p because you're doubling the principal. Substitute the known information. Divide both sides by p. That gave you the 2. Take a log of both sides, natural log, and then throw down that 12t. And then solve the linear equation. Among increasing functions, the logarithmic functions with bases b greater than 1 increase much more slowly for large values of x than either exponential or polynomial functions, right? I mean, if you've got a logarithm with base b greater than 1, like say base e, maybe we're talking about the natural logarithm, it's really slow to increase. When a visual inspection of the plot of a data set indicates a slowly increasing function, a logarithmic function often provides a good model. We use logarithmic regression on a graphing calculator to find the function of the form y equals a plus b ln x that best fits the data. So calculator would give us the a and the b that would give us a model that would fit data in that case. A cordless screwdriver is sold through a national chain of discount stores. A marketing company established the following price-demand table, where X is the number of screwdrivers people are willing to buy at each month, at a price of P dollars per screwdriver. So P is the price, X is the demand that goes with that, the number of screwdrivers produced and sold. And of course, the less expensive it is, the more you can sell. You can see data there. To find the logarithmic regression equation, enter the data into lists on your calculator as shown here. Okay, so we're going to go stat, okay, and then the cursor's going to be right there at lists, at edit, and then you can input the data. So you hit enter, and then you have your lists there, list 1, list 2. You're able to input the data. Of course, these were the data that we were given. Okay, X, that's the number of screwdrivers produced and sold. P is price, which is a function of X. So we could think of it the other way too, that X is the number sold is a function of price, but it works the other way too. Price is a function of number sold. Choose linreg from the statistics menu. So you're going to go stat, and then you're going to use the right arrow button. So stat, then the right arrow button, and then that puts you in the calc submenu, and then you're going to go to for, which is linreg, and hit enter. And if you have the data input, it will return a y equals a plus b ln x coefficients for a and b. And so those values of a and b substituted into this y equals a plus b ln x form will give you a logarithmic equation in two variables, which can be used to model the relationship between x and p. So the regression equation is y equals, after the substitutions, 256.4659 minus, and the b, okay, so negative 24.038 ln x.